In this video, I'm going to show you how to divide as fast as a computer. What we're going to first do is we're going to understand how computers add. We're then going to understand how computers multiply. We're then going to make a prediction on how computers will divide, except we're going to see that this does not work, and we're going to understand why it doesn't work. We're then going to introduce an alternative way of dividing, which is what the computers use, and then we're going to work out how fast this method actually divides numbers. So for how computers add, it's much like how we would add in base 10, except they're going to do it in binary. So we first start off with the lowest place, so the 0 plus the 1. We add it together. Is it equal to a multiple of 10? If so, we carry 1 over. If it's not, we don't carry 1 over. So 0 plus 1, well, that's equal to is equal to 1, which is not a multiple of 2. In binary, we're looking for multiple of 2 instead of multiple of 10. Now 1 plus 1 is 2, so we've got a multiple of 2, so it carries over. So we carry 1 over, and this becomes 0. 0 plus 0, well, that's just 0, so we carry nothing over, and we actually get 0 left over, so we get 1. And then 1 plus 0, well, that's going to be 1, and finally here, well, technically it's a 0, so it's 1. So this is how computers will add, which is pretty efficient. Now again, computers multiply in the same sort of way as we would expect with sort of by hand multiplication. So we start off with the lowest digit, which is a 1, so we don't get any zeros from this, so we're just multiplying this thing by 1. So we get 1, 0, 1, 0, 1, 0. Then we move to the next digit. Now, because this is the second one, that automatically starts at 0. Then we multiply it by the number that's here, which is just a 1, so we're keeping it the same. So we get 0, 1, 0, 1, 0, 1. And likewise down. So to this one, well, we're multiplying by 0, so this one's going to be adding 0. So we have a 0, 0, but then we're multiplying this number by 0, so overall is 0. And then finally, for this number, we've got 0, 0, 0, 3 zeros this time. And we're multiplying this whole number by 1. So 0, 1, 0, 1, 0, 1. And then we go through and we add up all of these numbers using the addition algorithm that we saw in just then. Now, this is likewise pretty efficient. Not really much efficiency gains you can look at. Now, when numbers get big, you tend to take different algorithms for multiplication, but for small numbers, this is the most efficient way. So how do we expect computers to divide? Well, the way you'd expect was kind of following sort of a bus stop method. So 7 down here, 81 in the bus stop. Then we work out how many times 8 goes into how many times 7 goes into 8. Well, that's only once. How would it do that? Well, it could do 8 minus 7, which is 1. So it's done it one time. And then we can do 1 minus 7, which gives us minus 6. Doesn't work. So instead we use this as the carry. So this goes to 1, like this. And then we determine how many times 7 goes into 11. So we have 11 minus 7, which is 4. 4 minus 7, which is minus 3, so it doesn't work. So 4 is now our carry. So you get 11 now becomes 40, because this would be a 0, and we only get a 1. And so forth. But you can kind of see this is quite inefficient. Say instead of 7 we were dealing with 3, and one of the numbers was, I don't know, 9. It goes in quite a lot, and we're going to have to keep repeating this for however many decimal places we want. So it's not very efficient. So let's have a look at how to find k divided by m. Well, what I'm first going to do is I'm going to write k divided by m as k times 1 over m. The reason I'm going to do this is we've seen that multiplication is very efficient. So instead of doing k divided by m, I'm going to do k multiplied by some number, and I'm going to calculate 1 over m. And we're going to see that calculating 1 over m is quite simple. So next, what we're going to do is we're going to let 1 over m be equal to x, where x is like some decimal number rather than a fraction. And then what I'm going to do is I'm going to divide by x and multiply by m. So I get 1 over x equals m. And then I'm going to bring everything to one side. So we get 1 over x minus m equals 0. Now at this point we can use a Newton-Raphson method. You're going to see why we choose to use it. So we have Newton-Raphson method as xn plus 1 equals xn minus f of xn over f prime of xn. Well, that leaves us with xn minus 1 over xn minus m over, now the derivative of this is minus 1 over xn squared. So pulling out the negative, we're going to have xn plus, multiplying top and bottom by xn squared, xn minus mxn over, and this will be just 1. And we'll simplifying this, we get 2xn minus mxn squared. That should be squared here, because I multiplied top and bottom by xn squared. So basically what we've got is a recurrence relation for this value of x. So if we choose a suitable start point, then this sequence will converge. Now you might be thinking, well, what's the point? We're approximating. Well, unfortunately, even when we do division of most fractions, we will approximate. We will cut off at some point, or we'll round the final digit. The use of this is that it converges much faster than our long division method will do. In a lot less steps and a lot less inefficient steps, this will converge to our answer. We're going to see exactly how fast it will converge later on. So let's have a go at an example. So let's find 1 over 3. So m equals 3. We have xn plus 1 equals xn minus, 2xn minus 3xn squared. Now we're going to choose a suitable start point. Your suitable start point has to be anywhere between 0 and 1. Notice that our fraction is a positive number, so hence the beginning 0, and 1 divided by something has to be less than 1. So we're going to choose our start point to be anywhere between it. In this example, I'm just going to choose 0.5. So let's have a look. What do we get for our values? x1 is going to be 0.25. x2 is going to be 0.3125. x3 is going to be 0.33203125. x4 is going to be 0.33332824771. And finally, x5 is actually going to be our famous 0.33333, where my calculator gives no more decimal places. So what we've done is we've found 1 divided by 3 in a very efficient way. Now you might be thinking, well, it's not very efficient, but if you try this by the long division method and you count a number of multiplications and you repeat this for the Newton-Raphson method, you'll find it's a lot quicker. Now this sort of gets expedited when we look at more complicated divisions. I think for 1 over 3 it will be very, very similar, maybe even long division beats it. But as you'll see with my proof later, this method is going to converge unbelievably fast. Okay, so let's calculate how fast this recurrence relation actually converges. Now, what I've got here is I've got our recurrence relation that we derived. I've got the limit of this recurrence relation, so it's going to approach 1 over a. That was what we designed it to do. And then I've got this limit. Now, this limit is kind of pulled out of a hat, but it's how you measure the rate of convergence of a recurrence relation. Now, we're not going to worry about this definition. I'm using this limit because we're going to show how many decimals we add, or roughly how many decimals we add with each iteration. Now, basically what this formula says is, as n goes to infinity, what's the biggest value of b, or beta, that I can choose such that this limit, which is the n plus 1th terms difference between the limit and the nth terms difference between the limit, what's sort of the rate of convergence, the highest rate of convergence, such that it's less than infinity. Now, in the case of this sequence, it's actually quite easy to work out. Now, you don't need to worry too much about this formula. If you want to look at another video on that, feel free. We're not going to use this definition. We're going to use this formula to derive something more powerful. So let's put everything in the limit. So I'm going to replace xn plus 1 with what we had at the top here. So we have 2xn minus axn squared minus x star, all divided by xn minus x star. Now ideally I'd be able to cancel the bottom somehow. So we would hope that on the top there's going to be a factor of x star. Now remember, x star is 1 over a, so let's actually replace this in. So we get a limit as n goes to infinity of 2xn minus axn squared minus 1 over a. And on the bottom we've got xn minus 1 over a. Now, quite interesting in that 1 over a is actually a factor. 1 over a is actually a root of the top expression. Why is it so? Well, remember, as n goes to infinity, we're expecting that it's going to be a limit, i.e. if I was to put x star into the top expression up here, we should get that it all cancels out. So putting 1 over a in, you're going to get 2 1 over a here, minus, well, this is going to be 1 over a, minus 1 over a. So the top will be 0. So we actually have a factor. And I don't need this less than here. So this is equal to limit as n goes to infinity. Let's take out a factor of xn minus 1 over a. Well, now we need a minus a xn squared. So we put minus a xn. That means these two multiplied together give us that term. Then multiplying minus a xn by the minus 1 over a, we're going to produce a positive xn, but we need one more of them, so I'm going to add 1. So we get 1 times xn, that'll get us the 2 xn's, and well, 1 times minus a is minus 1 over a. So this works. Let's add the bottom in. Now here's where the tricks get really interesting, because if I pull out a minus a on the top, so we do the limit as n goes to infinity, and I pull out a minus a. Remember, there's absolute value, so actually we can just get rid of the negative. Well, we're actually going to have an xn minus 1 over a, and this is going to be an xn minus 1 over a. So we're going to have an xn minus 1 over a squared, all divided by an xn minus 1 over a to the power of beta. And well, all in all, this is going to be the limit as n goes to infinity of a times 1 over xn minus 1 over a to the power of beta minus 2. Now, if beta equals 2, so this is what we call quadratic convergence, then the limit is going to be a. So the limit will be a, and I'm going to call this here L. Now, if beta is bigger than 2, what happens? Well, xn minus 1 over a is going to go to 0. So we're going to be dividing by 0. So we're going to get L goes to infinity. So the biggest beta that we can choose is 2. Now, why is this going to be useful for us? Well, what this means is, this limit up here, we can get rid of the limit sign. And we can rewrite this as xn plus 1 minus x star over xn minus x star squared is going to be roughly equal to some constant c for each value of n. we don't know what this is going to be equal to. We find that actually as n goes to infinity, this will be a. But when it's less than infinity, it's going to take a different value. So I'm just going to call it c. Now if I take a log on both sides, log base 10, we're going to have log base 10 of xn plus 1 minus x star over xn minus x star squared, and that's roughly equal to log 10 of c. And well, splitting the log up, bringing the log to the other side, and bringing down the 2 from this power, you're going to get that log 10, I'll just move over to the side a little bit, log 10 of xn plus 1 minus x star is roughly equal to log 10 of c plus 2 log 10 of xn minus x star. Now what does this mean? Why is this so powerful? Well, log 10 roughly says the magnitude in base 10. So how many decimal places are zeros? That's what log 10 tells us. Now this is the difference. This is the difference between what we have and our answer. And what we're saying is that the n plus 1th term is roughly double as accurate as the nth term. Roughly double as accurate. So this says n plus 1th term has double the decimal accuracy. As the nth term. Which I think is really, really powerful, because say we had, I don't know, we had one correct decimal place. So when n equals 1, we have one decimal place. Well, when we have n equals 2, we have 2 decimal place. N equals 3, we have 4 decimal place. N equals 4, we have 8. 5, we have 16, and well, just going up to 10, you have 1024, which is sort of a huge leap. Huge leap. So yeah, this is why this method is so powerful, because okay, for small number of decimal places, yes, it's not going to be that much more efficient than regular bus stop division. However, we don't always want a few decimal places. A lot of calculations, especially when you're dealing with computer science and physics and whatnot, you want a high degree of precision. So you want a lot of decimal places, and bus stop method just ain't going to cut it. And on top of that, computer's going to be doing thousands of divisions each second. My computer is going to be doing divisions as I make this video. That's just how it works. So you need each algorithm to be as efficient as possible, and this is how they do it.